So this slide pack is from this Jason Mays guy at Google. It's actually a really good slide pack. I wouldn't be able to make one this nice. So let's just see how far we get today. And yeah. So what's artificial intelligence, machine learning, and deep learning? Artificial intelligence is a science of making things smart. It could be defined as human intelligence exhibited by machines. It's essentially a broad term for getting computers that perform human tasks. The scope of AI is disputed and constantly changing over time. So, the systems implemented today are a form of narrow AI, a system that can do just one or a few defined things as well as or better than humans. Recognizing objects, gestures, we trained it to learn. When we say train, it means that we need to write code to identify and learn from information. I mean, if you look all around, you have examples of essentially machine learning or AI. I call it machine learning usually. So what can we use AI for? Object recognition, right? You've seen that classic example when they move around that tennis ball and you can see it tracking. I think one of my seniors did it this year in senior project. That was a pretty simple, it's a very simple algorithm. And oh yeah, we had it last year too, but that one wasn't so successful. You have speech recognition and sound detection. So, you know, if I pull up Google Translate, and essentially type it or say something, it's essentially following some sort of Markov model and predicting what it thinks the word is going to be, right? So you have something like, like in Asian languages, they're very tonal, right? So you say one thing off and it becomes a completely different word, right? So you can use context in a Markov model or something to kind of figure out what is this person actually saying, okay? Natural language processing, sentiment analysis, something that's missing this term, and I think a lot of people are bothered by it, is this person sending this email to me, are they angry or are they sad or are they happy at me? You can't tell, right? There's a lot of missing contextual information this term, which is driving a lot of people insane. Learning to draw an image, predicting. So predictive modeling, like, are the stocks going to go up or down based on this data set? Obviously, there's no machine learning algorithm that's going to predict it right now very well. We can predict the next word in a sentence, right? People usually speak in a very fixed manner. Translation between languages, okay. I wonder if this will, should probably do this example. I did this example in the last class. Let's do it again. Why not? We have time.
Okay.
I don't really have anything planned out much. Essentially, this is just some extra stuff that I'm throwing together because, frankly, doing that FPGA stuff over remote debugging it's not going to be fun, and we don't even have licenses to do some of that. Okay. Let me see if I can switch to camera. Can you see my phone?
Yeah.
Yeah.
Oops, no.ครูกับนักเรียนโรงเรียนนี้คุณภาพต่ำจริงๆ
Teachers and students of this school are really low quality.
Oh my god.
Well, there was a mistranslation there. It said low instead of high. It's kind of weird.
So I speak Thai too. So essentially, we're trying to model a sentence, the sentence structure, and my friend actually works for the natural language processing group at Amazon, but he wouldn't tell me anything. So, but you know, here's another thing with context, right? Let's try something like ผมรักเธอ
I love you.
right?
We love you too, Kevin.
No comment.
Lay it back.
But now listen to that. I said ผมรักเธอ ไปตัดผม
Go to cut the hair.
Right. So the word pom is contextual. Pom can mean hair, and pom can also mean eye, the male form of eye in Thai. So the AI we can actually model some of this behavior so that we improve the detection for, let's say, speech recognition translation, right? And that's essentially what it's doing there. In fact, here's another example. Asian languages are very tonal. So, ma, 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 ma.
Come.
Oh, no, don't. Okay. It didn't pick it up. It didn't pick it up. But if I say, by key, ma,
Go horse riding.
by jung ma,
Go to lead the dog.
ma ตรงนี้
Come here.
Right. So when you put context into the case, if you put contextual information together, you'll get better accuracy. And that's essentially what we're doing with AI. We're gathering all this different data and kind of smushing it together in a somewhat intelligible way to create things like translations, predictions. One other thing I do for my embedded security class is essentially we do a predictive model, right? Think about Dr. Lin's classes. Back to Dr. Lin's classes, we have essentially, it's all assembly and, you know, stuff like that, and architecture and instructions. You know, if you look at a program on a computer, a sequence of instructions, an algorithm, you'll see that different programs have different distributions of instructions, right? This program has more XORs, this one has more AND instructions, okay? So you can actually perform a model. You can generate a model so that you can predict what the instructions that's going to come next. And that's pretty useful for things like, for me, for side channel analysis in my research, or something like branch prediction, right? You could use it for branch prediction. So yeah. So restoration and transformation, taking an image and using machine learning to figure out what it should be, or generating faces based on what it knows a face should be. Machine learning is an approach to achieve artificial intelligence through systems that can learn from experience to find patterns in a set of data. Okay. Sometimes that set of data is extremely noisy, and you need to perform some additional techniques on it. Just like when I said there were 4 tones, 5 tones, there's 5 tones in Thai, horse, and if you said a different thing like horse, it turns into horse, or come here, or a dog, right? So it's essentially teaching a computer to recognize patterns by example, rather than programming with specific rules. So the patterns can be found in data. Machine learning is about creating algorithms or a set of rules that learn complex functions or patterns from data and make predictions on it, form a narrow AI essentially. And you can reuse these systems to recognize other objects with new data. So you can take some data in to train the system. You take data sets in to train the system. You learn patterns from the data, and you classify new data it hasn't seen before. Okay. One popular thing to do on FPGAs, if we take it back to the actual course here, is neural networks on FPGAs, or convolutional neural networks, which is a form of machine learning. Okay, so beauty of ML, let's see here. Okay, so the machine learning system can then be reused for future objects without actually having to rewrite the code. So, you know, we're used to the idea of if, else if, else if. Here's the machine learning program. Let's try to classify things and change ourselves to reduce the error rate, right? So deep learning, I'm not really into deep learning, so I don't know what this is. Technique for implementing machine learning, okay. Deep neural networks, which you may have heard of. Oh, all right, and we'll explain it later. So apparently it started off with artificial intelligence, machine learning, and then deep learning. Okay, so what do we do actually when we want to start out using machine learning? The most popular data set is the iris data set from Fisher back in like 1936. So that data set's pretty popular to use because it introduces you on how to use you know, let's say the sklearn library. Sklearn is a machine learning library you can use in Python that's pretty powerful, or at least for me, pretty useful. So features are attributes that are used to train a machine learning system. They're essentially properties of things that you're trying to learn about. This orange has a weight, it has a color, and he spelled color correctly, which is great. It might have a size. The size of the orange might be different depending on what type of orange it is, what family it is. The shade of orange might be different. The texture might be different as well on the skin, depending on the type of orange, right? So these are all features or attributes. For human, you could have intelligence, you could have hair color, you could have eye color, you can have a bunch of different attributes or features, and each feature or attribute represents a different dimension of data. Essentially, a color of an orange could be one dimension, the weight of an orange could be another dimension, and essentially the skin texture of an orange could be another dimension. Okay. So here he goes over in 2 dimensions. There's 2 dimensions of data here, right? The weight and the color, okay? And if you're classifying citrus, you'd have yellow, you'd have green, you'd have orange, you'd have, you know, different colors or different shades of them as well. So if there are 2 features, essentially in this case, color and weight, there's 2 dimensions, okay? A 2D system is nice because it can be plotted in 2D. So essentially now what you could do, this is a simple linear regression, is you essentially separate the data set into essentially clusters, or in this case, anything above this line is going to be an orange, everything under it is going to be something else maybe, okay? So the classifier, the most basic form of classifier is just a line going through on a graph. Right? Everything above this line is a certain thing, everything beneath it is something else. So choosing useful input features can have a big impact on a machine learning system. What they're saying is some features are more useful than others. If you're trying to look for something like, well, in this case, ripeness and seed count don't let us distinguish any distinguishing factors for the fruit. You have to, one of the things about machine learning is selecting the most appropriate features. Now, there's something called the curse of dimensionality, where you have too many features, too many data, and the bad data overwhelm the good data that will help you classify, let's say, fruit in this case. You have too many dimensions of data. First of all, it slows down your system. Second of all, it reduces your successful classification rate. Oops. So, 3 dimensions of data. To separate the data meaningfully, we could do a 3D chart and separate the clusters of points with a plane that divides the 2 sets of data as shown. So most machine learning problems have even higher dimensionality, 20 dimensions, millions, right? So essentially what you need to do sometimes is reduce the dimensions of data. You use a different classifier then. You might not, oh, you don't know about KNN yet, but you might use something like a linear discriminant analysis where part of it is to fold 2 dimensions into 1 dimension, but while still keeping the data, okay? So, oh yeah, adding more dimensions can help separate out the data points, allowing the machine learning system to split the data up into groupings for classification. So too many dimensions can lead to, he calls it overfitting. It's also the curse of dimensionality. Too many dimensions means what you might end up doing, well, they're 2 different things actually. The too many dimensions leading to overfitting means your sample data is so close to the actual, to the sample set data is so many dimensions, and it's the model, the machine learning model is formed to that specific data set, and it's so specific to that data set that it's never going to be essentially able to classify data that might be a little bit different, right? So what you have is a training data set and a test data set. You usually split it up into, use this data to train, it's been classified already, then you run it through with a test data set and see how well and how different the train and test data sets are. So here, 1 dimension is too hard to split. 2 dimensions gives you better separation. These are adorable, by the way. So there's easy separation now, right? It might still not be that accurate, but adding more dimensions up to a certain point improves your data. So data hunting. The biggest challenge is finding unbiased training data for all those features in a format that can be fed into a machine learning system. So if you want to recognize cats, the more data you have, right? If you have 10,000 images of cats, you might have a better chance of getting decent results than if we had, let's say, 100 images. Your classification rate might be better, okay? So it could be data in tables with multiple features, text, sensor recordings, sound examples, whatever you're trying to classify. Classifying is not the only problem as well, but I think he goes into the slide pack a little later. Okay, so teaching a machine learning system. So even if you have 10,000 cats, if they're not different kinds, you could end up with a problem. Yeah, and this brings you back to that, what was that machine? Like, you can design a system to be, you didn't intend for it to be something like to discriminate against someone, but you might end up designing an algorithm that discriminates against someone just because your data is maybe biased in some way. Okay, so here, 4 black, 10 kilogram dog, 2 orange, 5 kilogram chicken. Okay, if you present it with a cow, 4 legs, black, and 200 kilograms, it would predict dog now, because it only knows dogs and chickens, and it was the closest match, right? Well, I haven't decided how to do this. Why don't you, if there's a video in this class, I don't want to use this time to view it. Why don't you go view these videos on your own? So supervised versus unsupervised. Essentially, supervised means that the algorithm, you're feeding it prefab data. You've classified it already for it. You've trained the data yourself. You have gone through manually and populated and said, this is a dog, this picture is a dog, this picture is a chicken, this picture is a cow, this picture is whatever, right? So you essentially, supervised learning starts off with labeled data. You know what you're starting with, okay? You're telling the system, this is what it is. This is what, this red apple, this is an apple, it's red, it's this weight. Now, contrast this with unsupervised learning. Unsupervised learning is essentially saying, the system will figure itself out, right? We're not going to provide any training, right? We're not going to provide any training data for the system. Let's just go with what we, let's just go with, well, let's just train you on the job, essentially, is what you're saying. So the machine essentially learns from an unlabeled data set, okay? So you don't have labels, but if the label has some unique properties to it, let's say in this case it's two-dimensional data, and you see clusters forming, well, then these clusters, maybe we can take into account that these are the red apples over here. It might not know that's an apple, but it's going to group all the red apples together, all the green apples together, and all the oranges together. It might not know what they are, and it might not have had prefab data, but essentially in unsupervised, you never actually feed in trained data sets. Okay, reinforcement learning is learning by trial and error through reward or punishment. Program learns by playing the game millions of times. We reward the program when it makes a good move. Essentially, this is essentially exactly how your brain works. If you reinforce good behavior, like handing things in on time and going over, like reviewing and taking notes and stuff like that, you essentially reinforce those good behaviors. But let's say something like you have bad thoughts and you keep replaying those bad thoughts in your brain, it reinforces the bad neural pathway, right? So that's what reinforcement learning is. You get a reward. The only way to win is not to play. What is that? So there are many ways in which a machine learning system can try and learn patterns to classify data presented to it, okay? And you know, machine learning systems, they definitely use more than 2 dimensions of data. I'm actually working on a research project right now, which is my PhD, where we're kind of trying to figure out the same type of thing here. We're using machine learning techniques in the microprocessor realm, the side channel realm, and you can see from this graph, these are instructions. The instructions, the type of instructions, depending on what the waveform looks like. Well, let's say here, you pick off a point in the waveform, you know, it'll cluster a certain way.
I don't
Okay.
think we can see
You
it.
can't see it.
What?
We cannot
Can't
see
see
the
it.
graph.
Like this? What can you see right now?
The slide packet.
Oh, it must just be sharing the slide packet. All right, sorry. Well, I'll show that in let me see if I can try to share. Oh, it is only sharing the slide packet. Can you see that?
Yep.
Yeah, so I was
Yes.
just using KNN or some clustering algorithm, or it's not a clustering algorithm, but you see that the machine learning, and it's very basic form, but you can see that the instructions, let's go back here. I plotted the instruction. This is a instruction trace, and I've essentially classified each instruction group, and it's clustered into groups. You know, the algorithm might not know what this is, but it knows that there's a cluster of them. Okay. Oops. And can you, let's see, resume share. Can you see the slide pack now, the green slide pack? Yes, no?
No.
I can't.
Okay, you share. How about now?
Yep.
Okay, great. Hayden, you have a question?
Yeah, so how does so when you want to reinforce, like let's say I want to maximize points,
Yes.
and how do you reinforce behavior on a machine learning system? So like if it gets a lot of points, you reinforce that.
Well, I guess in a neural network, the paths, just like your brain, the paths that get used the most often are the strongest, right? So the weight of that path will probably be heavier than the other paths. So essentially what I'm saying is you use it more often, it's going to be higher on the priority list. I don't think that really answers your question, but I think if we go through the slide pack, I think it'll answer that for you.
All right.
Okay. So here is an example 1 where you draw a line of best fit in high school, right? And he says this is really an example of a machine learning system, right? It's essentially a regression, okay? Predict, given X, what the Y value will be, even for unseen examples by extending the line further. That's a regression. What we were talking about earlier when we were classifying orange versus apple versus cat versus dog, that was a classifier, right? Okay, that's a classification problem. This is a regression problem. And essentially what we want to achieve is a machine learning program that calculates these lines by themselves, right? So we also have the idea of outliers. Outliers are not great. They're not that great because we have blue dots here and the outliers here with respect to, let's say, this this linear regression here, right? So this outlier is not where it's supposed to be. It's going to reduce the classification rate. Over here, we see that here that it might not necessarily be a line. Okay, it might not necessarily be a line. Okay, it might not be a straight line. So this is your k nearest neighbor classifier. The k nearest neighbor class, and he spells neighbor right too. I like this guy. So the k nearest neighbor is saying, okay, we have things that are similar are going to cluster, are going to be seen near each other. So k nearest neighbor means look at my 5 closest neighbors, or 6 closest neighbor, or my closest neighbor, 1 NN. KNN could be 5 nearest neighbors, 3 nearest neighbors, 7 nearest neighbors, right? How many people are close by me? I'm going to classify myself as the same thing, okay? Oh, neural networks. I'm not good at this one, but let's try to get through this slide. Okay, so 86 billion or so interconnected neurons. Each neuron responds to certain stimuli and passes output to another. There might be a bunch of them dedicated to recognizing cats, each having a different weighting for the overall contribution. If all those fires, the brain tells you that you saw a cat. In a machine learning, artificial neural networks, loosely modeled on the brain, are used to calculate probabilities for features they are trained to look out for. So there's going to be multiple layers. And neural networks are actually expensive. I think compared to things like a simple linear regression or a KNN classifier and all of like that type of classifier, neural networks use a lot more time and memory. What you're going to see, and I don't know if I'm going to get into this, but because I'm just kind of flying by the seat of my pants with this lecture, is you'll see some techniques in machine learning. It's essentially a balance, right? How well does this classifier regression work? How well does this classifier regression work? But the other two things is, how much memory is this algorithm using? How much memory does this machine learning algorithm use? And how much time is it going to take to process my data? Is it going to process my data in time such that I actually get an answer that can be used like before it's useless? Okay, so neuron has a bunch of weighted inputs. Take the number and multiply by the weight that are summed together. A bias is then added to this total. The weights and biases are determined when we train the system. If final result is greater than the threshold, it activates, providing an output. The strength of output depends on the activation function chosen. The output is then fed into other neurons in the other process, and the process repeats. So you might have a network of neurons, right? And does this neuron activate? It depends. Given some information, if the threshold and the weight is high enough, there's essentially an activation that occurs. If it activates, it might go and activate another neuron, okay? So this is a really common problem where they try to classify the number 0 to 9, right? And this is, honestly, I wanted to make this one of the labs, but I mean, how many weeks do we even have left? 3 weeks? It's not enough time. I was going to try to get you guys to do this in OpenCL this year, but it's not happening. So this is a multi-layered perceptron. Based on my working with just running the basic algorithm, it's a little bit slower than some other methods. Actually, I have that on my other slide pack I can show you later. But this is a deep neural network. It's one of the oldest forms of neural networks. And each layer is fully connected to the next, and data flows forward only. You know, if you actually look at a lot of this stuff, a lot of these things can be traced back. You go back to digital system design when we were talking about state machines with discrete transition probabilities. X equals 1, we're going to go to this state. X equals 2, we're going to go to this state. If you think back to that and come back here, it'll make a little bit more sense to you, right? These are circles, these are arcs. How do we transition, right? In this case, the transitions may no longer be those fixed conditions, x equals 1, x equals 2, x equals whatever, right? So you got a lot of inputs, you got neurons. Do they activate or not? There's that formula, that input function of the inputs. Does this neuron activate? If it activates the next one, right? Or it feeds into the next one and it feeds forward until, this is the input condition, you reach the output layer, right? The output layer, there might be multiple layers here. The output layer is going to say, is this number between 0, is this number a 0, 1, 2, 3, 4, 5, 6, 7, or 8, or 9? Okay, so deep neural network simply consists of many layers between the input and outputs. The hidden layers are typically of lower dimensionality, so they can generalize better and not overfit to the input data. So dimensionality again means what? Dimensionality, dimensions of data. This orange weighs this much. This orange is this color. This orange has a diameter of blah, blah, blah. The texture of this orange is whatever, okay? And overfitting is essentially when you have the input data and the system only detects based on that exact input. You don't want it to always just activate on that one input. You want it to have some leeway, so that'll activate on essentially some similar stuff. If you have it trained exactly to that model with like hundreds of dimensions of data or something like that, it's going to only lock onto that one. It's only going to lock onto that one example. You want to be able to generalize, which is why they're saying use these middle hidden layers for that. And here's another one. Go watch it on your own. This one's actually pretty good. Here's how convolutional neural networks work. Okay, so you got a couple different, we talked about regression. We talked about classification. Excuse me. We talked about clustering. Oh, we didn't talk about, we kind of talked about clustering. And there's all, we talked about all of them. Sequence prediction, right? What's the next instruction that's going to occur, right? Branch predictor is an example of what you could use sequence prediction for. Regression, right? Predict the numerical values. Classifier, is this a human? Is this a dog? Is this an apple? Is this an orange? With clustering, you might, for my research example, you would cluster similar instructions. What is this? The machine learning system is outputting a decimal number. So given some input, you get some numerical output. For example, if an orange weighs 200 grams, its radius is 4.2 inches. The output here is 4.2, and this is what the machine learning system is trying to predict. The linear regression tries to fit a straight line to the example data. Okay. So classification is about determining the class, right? In my research, I'm trying to determine, is this a store instruction? Is this a load instruction? Is this an add instruction? Is this an XOR instruction? So my inputs in my research would be the actual the actual side channel information, the power signature on a microcontroller would be my input. And the output would be for that one clock cycle, is this an XOR, is this a load, is this a store instruction? So essentially the output's a label, unlike the previous regression, which would have been a number. Oh, and a probability estimation. Okay, this means that the output of the machine learning system is some decimal number between 0 and 1. Okay, so probability estimation, it's like that previous example I talked about in the start of class where I said those words, ma, and ma, right? What's the probability that it's ma, or what's the probability that's ma, or what's the probability that's ma, right? So there's different outputs essentially. Oh, this is funny. If we are 80% sure what we see is a cat, maybe we want to feed it. If we are 75% sure, we might want to wait until we're more sure, or we can use we can improve the model by using more contextual information, such as a hidden Markov model or some sort of Markov chain to improve our rate, right? Okay. Let's see, regression. Regression is concerned with iteratively monitoring the relationship between variables using a measure of error in the predictions made by the model. I encourage you to go back and review the videos in the slide pack. They're pretty good. I just don't want to spend time on them here. I mean, I don't know if any other teacher is doing the, has anyone else talked about the split classroom or the flipped classroom with you?
Not any of my teachers, no.
Oh, figures. So the flipped classroom model is essentially leave the boring lecture stuff that can just be regurgitated and make you essentially review it on your own, pre-record those videos, because it's, you know, and then use the class time to answer questions and work on actual problems. So it's been a model that people have proposed. The problem with that model in education is students don't actually go and review anything before class. So that's where it falls apart. Anyway, back to machine learning. Regression methods are a workhorse, blah, 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 blah. Oh, straight lines best fit are a form of linear regression. Oh, instance base, K nearest neighbor. I use K nearest neighbor a lot because it's cheap. It doesn't scale well for a large amount of data though. Now, when we talk about KNN, again, when I said KNN earlier, it's like, look at my 5 closest neighbors or my 2 closest neighbors. The problem with KNN is if you have 20,000 data points, you're going to want to calculate, you're this data point here. You have to calculate the distances to every single point in your space. If you have 10 dimensions of data and 20,000 data points, that's going to take quite a while for the algorithm to go through every single point. Now, no one actually does that brute force method anymore where you go through every single point. You actually have, I think it's called, it's a tree model where it caches values, right? But think about it. If you're using Pythagorean theorem to figure out the distance, or Euclidean geometry to figure out the distance to 20,000 other points in 10 dimensions, you're going to take quite a long time. So it's not necessarily always the most efficient. It always the model that you pick completely depends on the data set that you have. Oh, decision trees are pretty straightforward, right? It's like, do we go this way or do we go that way? I bet those of you who have had to take data structures are probably not fond of trees by this point, or linked lists.
They're not too bad.
ABL trees or red-black trees?
ABL's different.
Huh?
Binary trees and linked lists are fine by me. ABL tree is taking way too much of my time this term.
I was reading something very interesting, and for an interview, I was on some interview question forum, and they were saying if someone's asking you to reverse a linked list or something like that, you're missing the point, because if you have to reverse a linked list like that, then you probably did something bad and it's probably not well designed anyway. A lot of the interview questions that you'll see are just dumb. Oh, Bayesian. Okay, Bayesian methods. Gaussian naive Bayes is another classifier approach. It's essentially Bayes' algorithm. I don't remember it off the top of my head. It's like probability of B given A is equal to probability A times probability of A given B divided by probability of B, something like that. Okay. So clustering again. Oh, yeah, you have k-means and k-medians. I don't remember what this is. Association rules. Extracting rules that best explain observed relationships between variables and data. All right. Artificial neural networks, that you saw that example where we went through and tried to classify the number 0 to 9 depending on those inputs. If we go back there a minute, so what they're doing there, so this 28 by 28 pixels, you could essentially break it up by pixel here, right? You want to know 0 to 9, what's the most likely output? Yeah, we have the layers, we have the neurons, we have the activation. Does this neuron activate or not, depending on all of these inputs? How do we get these inputs? I forgot to mention this. That 28 by 28 pixel, each pixel is a unique color, right? In this case, it's black and white. It's a unique grayscale value. So whatever that value is, each pixel, if it was represented by 256 values, would be an 8-bit value. And those could act as inputs, right? The shade of each pixel could act as an input. And then you train on that information. Oh, Bayesian. So Bayesian was Gaussian naive Bayes. Gaussian means you have that normal distribution. And then again, I don't remember, probability of B given A is equal to probability of A given B times probability of B over probability of A, or something along that line. Clustering, association rules, artificial neural networks, deep learning, convolutional neural networks, and multi-layered perceptron. Convolution neural networks actually performs convolution. Like if you work in audio, you know that you take two signals and you can convolve them together to form this output signal. You convolve an input signal with its filter, and then you get the output signal. You're essentially performing the same convolution within the neural network as well. Dimensionality reduction. So there's something called principal component analysis. I use linear discriminant analysis, but it's the same idea. You have 10,000 dimensions of data, right? If we have 10,000 dimensions of data, are those 10,000 dimensions of data always useful? No, some of them aren't, so we can get rid of them, or we can kind of fold them together to reduce the number of dimensions. Reducing the number of dimensions essentially reduces the amount of information. Reducing the amount of information reduces the amount of processing you have to do, okay? So some methods like LDA, linear discriminant analysis, you have dimensionality reduction. You can build it's kind of you can use it to reduce dimensions and classify data at the same time. Something like a KNN, I don't think you can do dimensionality reduction just with the KNN. You have to apply something like principal component analysis. What they're saying is some dimensions of data have more relevance than essentially other dimensions of data. You might not care. One dimension of data that you might care about when buying a car is your MPG. Or what else could you care about? Horsepower. But honestly, maybe the dimension that says color of the car doesn't really matter to you. So that dimension's not that useful. But you might still want to take it into account because you don't want to, let's say, what's a bad color? You don't want your car painted in Pepto-Bismol pink and brown. So it could still be a dimension. What is this? I don't know anything about this. Ensemble methods are models composed of multiple weaker models that are independently trained and whose predictions are combined in some way to make the overall prediction. Oh, I actually did this. I didn't know this, but you hear some boosting algorithms. This is what they do. But Ensemble, essentially what I did to calculate grades one term was, because of the coronavirus last term, I essentially just used a couple different models together to predict everyone's grades. So I guess that would be an example of an ensemble model where I used a couple, I think I used a regression, and I did something else. I don't remember what else it was called. I did a regression and something else to essentially try to predict the final grade without students actually taking the final exam. Okay, and that model was about 80% accurate, so it wasn't that bad. You can actually achieve pretty good classification and regression outputs with a lot of these algorithms. Oh, we're getting to the part where Google specific stuff, because he works at Google. Yeah, they use it for everything. They pretty much spy on you. We just use the Translate app, so that's an example. So yeah, essentially everyone's using machine learning everywhere. Robotics, Tesla is definitely using machine learning to detect the difference between a traffic cone and a pedestrian. But remember, when you use machine learning, you're never 100% sure of anything, right? So there's a 99% chance that that is a traffic cone versus a human being. There's still a risk that you're going to get the model wrong, right? There's no 100% guarantee. Like machine learning algorithms, and I think this is why they don't like them. It's not determined. It might not be. It's not as deterministic necessarily as a fixed model system. Like this definitely wouldn't work well on a space station or something mission critical, where you have to take inputs in real time, and if it fails, if there's any probability or chance that it fails, you're screwed, right? Which I guess that's why people are so concerned about self-driving cars.
Yeah. How do you know it's not a human being dressed as a traffic cone?
Well, you have to. It depends on what model you're using, right? You have to train on different models. But the problem now is how much you have to store. You have to store that information. It's a lot of this is a trade-off between the time it takes to process versus when you need the output. If you need the output now and I get the answer 10 seconds later, then it's completely useless. How much data are we using or processing, right? How much data do we have to process? You add 10 extra cameras, you add 10 extra dimensions or more of data, right? How quickly can you process that large increase in data, okay? I think we're pretty much done. Does anyone have any more questions before we go?
Yeah. So does the machine learning class at OIT count as a hardware elective or embedded elective?
The machine, not technically, but Troy and I will override it.
Okay. Because it works for the math minor as well, if anybody's interested.
So that class is much more math heavy than machine learning. It's machine learning, but it's very math heavy. Just be aware of that because it's a math class. Any questions before we go?
So I guess what's the plan for the rest of the term then?
Oh, I don't know. Well, let's go take a look. before we go, it's, oops, that's my taxes. Hold on. Did anyone try to access the school website yesterday?
Yeah.
Yeah, not good.
Yeah.
Okay, so this is the plan for the rest of the term.
Can't see
There's
it.
what?
You can't see it.
Oh, I'm sorry. Can you see it now?
Yep, we can.
All right, so you have, I'm gonna essentially do 2 labs with machine learning. We're gonna have a machine learning quiz, a VHDL quiz, FPGA architecture quiz, VHDL conversion lab. We're gonna have a little bit more lecture on machine learning on Wednesday, and then no more lectures for the rest of the term.
Okay.
Any other questions before we go?
Do you have a meeting right after this?
I do.
Okay.
My question is just we're gonna have normal office hour times for you, or
Yeah, so what I'm gonna do is this. For the rest of the term, I'll just use what would have been the class time as office hour, additional office hour times. So just
Okay.
log into the office hour link, okay?
okay. Thanks, Kevin.
I'll see you later. Bye.
Bye.
Bye.